All right. Well, welcome to the last lecture of the semester for 327, and might be the last lecture for you this semester. I don't know. Um, well, um, it's certainly been quite a change from where we started and where we end up here. So hopefully, I will actually be able to see you in person at some point next semester, and we're going back to gradually to normal operations. So, um, the plan for today is to kind of wrap things up, and we kind of um, lost a week of instruction and kind of went over more detail on certain things that I thought were important, like Project 3. So we're a little bit behind wrapping things up. So I don't know how coherent the lecture is going to be. On the plus side for you guys, whatever we're talking about uh, material-wise here today will not be on the final exam, so I will not test you on anything that we cover today. Um, Couple of announcements to start. I did make an announcement yesterday about the final exam format. So we'll be on Gradescope again. And once again, I'm just going to give you a large time window when you can start the exam. So please pick one where you're undisturbed and have good network connection and all that. It seemed to go pretty well for exam 2, so hopefully we're not going to experiencing any big difficulties for that one either. I do want to point out again, though, that I am expecting you to draw state machines and kind of upload these as part of the questions on the exam. So the finite state machine designer website that I have been using in class would be my recommended choice. It is up to you, but I will not be accepting any hand-drawn and then photographed or scanned-in images because I need to be able to clearly read and see what's going on. Um, so that was the first announcement. I'm just gonna switch to sharing my desktop now. Get that out of the way. Let's get my chat window up. Um, so second announcement was about Project 3. So I posted a clarification on these operators here on Piazza, so you can look at that. So I just want to point out because minus and division, they're not commutative operators. So the order in which you apply the operators actually matter. And I've had several questions and clarification questions from you about that. So what this all means essentially is that, well, if we have our evaluator here and we type 3, 1 minus, then the result should be 2 and not minus 2. Similarly, when we have 1, 2 divide, the result should be 0.5 and not 2. So I just want to make sure that everybody understands that. If you've already submitted and this is an issue, then please fix it and resubmit by Sunday. Okay, I think that's all the announcements that I had. Are there any questions before we kind of resume operations here? All right. So, so we're gonna do two things today. We're gonna wrap up Turing machines. So we've got this universal Turing machine stuff left. And I'm not going to explain this in too great detail. I'm just going to run an example and point out some things. So there's going to be a lot of hand waving over some details that if we kind of drill down, it would take a long time to explain that logic. And then, like I said, we want to wrap up. So wrapping up kind of means actually kind of coming back and, well, why are we even talking about these Turing machine things? What kind of relevance does that have? And we're kind of now exploring the limits of computation. So, so the whole P versus NP thing, which you might have heard before. So I'm going to try to explain um, in the minutes that are left to me um, what is going on there, and how this then applies to all the stuff we've done in this unit. Okay, so I kind of motivated these universal Turing machines before, and well, it's actually, there is a universal Turing machine which simulates other Turing machines. So it's a Turing machine that takes as input the definition of another Turing machine and an input, and then runs the computation. So it simulates the execution of M on input W. Um, and in order to do that, I kind of said we had to encode stuff. So the green stuff is the Turing machine that we want to simulate. So if we have an input alphabet of 0 and 1 and a tape alphabet of that and more symbols, then we would just encode these. Just take some bits. So however many symbols we have, 6, we need 3 bits. And then we're just going to arbitrarily assign some numbers to them. So we can then say, well, an input to M that might look like this, and this is the example we have been using, and I'm getting a "your internet connection is unstable" message, so please let me know if it's getting bad, and then I can maybe switch to my phone's hotspot, which may or may not fix that. So we can take the input to M, and we can kind of, there we go, convert that to an input or part of the input for U. And we're just going to introduce different symbols for U's tape alphabet, the brackets and the separator thing here. And we can then see, if you look up the encoding, that these are kind of equivalent encodings of the same thing. We also need to keep track of which state we are in. So however many states there are in M, in this case 7, we still need just 3 bits for that. We can just assign an arbitrary number to each state. And then what is left is a way to actually specify the definition of the Turing machine. And that can be done by these, I'm just looking if there's a name to these transition states. So whenever in M we have a transition like this, we can then say, okay, reset, that is 100. And then on the dollar symbol, so dollar symbol is 011. On the dollar symbol, so that's whenever we are in this state and we're seeing this symbol, then we get another special tape alphabet thing. Then we're going to transition to this state. And this is actually a mistake in the notes here. There is no state 001, as you can clearly see. What they really mean is the start state. So this should be 111. So we're going back to the start state. We're going to write this symbol, which is the dollar symbol, and we're going to the right. And that kind of represents this. And we can then just have a bunch of these in kind of parentheses. So this whole thing describes the entire transition function delta of this Turing machine. And this here is just there to actually kind of have an anchor for everything. And essentially this, together with this, uniquely describes M and W. So how can we now simulate the execution of M with this information on a tape? So first of all, we're gonna, if you read all this, then we're gonna kind of make the assumption that we actually have two tapes available. So one where all this is located. So so this is M and this is W, and it just makes it easier to not have to have one tape and kind of seek back and forth, moving the head around. It would just be very tedious. And I've already mentioned it doesn't really matter how many tapes you have. You might just be quicker that way, but you're not getting any additional computing power by adding a tape. So we're going to assume that all this stuff here is on one tape. Trying to remember which tape, what are they calling that one. And then we're going to keep the configuration of the Turing machine on a different tape. So this is going to represent the configuration of the Turing machine M. And essentially it has the start symbols. So if you look at W, wherever that is, it's 001, 001 for, so that will be the 0 symbol, 0, the 1, the 1, the 0, the 0. So we're going to have these symbols right here, but we're going to store some additional information. So these are just, it's essentially the starting string, what I'm highlighting here. But we're going to further say that whenever this thing here is not all zeros, so you can see only one of these tuples has a non-zero entry here. Everything else is 0, and technically these are the reject states. But only one is non-zero. That means we now assume that the head of the Turing machine M resides on this cell of the tape. And we are currently in this state. So if it's 0, if it's not 0, then this is the current state we're in, and this is where the head is positioned. So it kind of means here, okay, we're in the start and we're seeing the 0 symbol at this point. So, so if you were in this configuration, just as a different example, we'd be in the reset state, we'd be at position 3, 0, 1, 2, 3. So you would have to put the reset state here, and then the symbols would be encoded as follows. So there's a whole bunch of copying rules now that we could go through, but I just want to do an example on what the Turing machine is actually doing here. So given essentially this on one tape, and this is our initial configuration. So the Turing machine actually computes that from this. So on our working tape, we have this. So I copied most of the stuff. So we are here. And technically, the head of U actually resides here at this point. Right? It's U is a Turing machine, and this is what the working tape contains. So what it needs to do, it needs to find a non-empty state, which will be this, right? Everything else is, well, the non-reject state. So it needs to recognize this. And then it needs to come back here, and it now needs to here look for a rule that matches this left-hand side of this overall, sorry, that matches the current entry. And in this case, so we now have to seek the second head, and we would then have to compare and compare and compare. And we would find, okay, this is a match. So what now needs to happen is the Turing machine now needs to copy this information. I'm just going to copy. Actually, let me make a copy of this and work on that. So we need to copy this stuff here and write that here. And that now took care of overwriting the tapes. Instead of a 0, we now have a 1, right? This is the 0, and this is, oh no, we got a dollar. We were crossing it out. So we got a dollar sign here now. And now we also need to see where we need to go. We're going to go to the right. So we now need to take this new state, copy that one cell to the right, and overwrite this with the zeros, and then we're going to return the head here. And now we're just going to repeat all this until we are in an accepting state. So again, we would now seek the cell that has a non-zero entry here, so that'll be here. We will then here have to seek to a rule like this that matches that. So that was this. We're going to copy all this. Essentially stays the same, but the Turing machine doesn't know that. We need to go 1 to the right, copy this new state over, like that. Clear this, and go back here. And that's all we need to do. And my claim now is, when we're done here, then we have accepted the string 001100 as being part of the 0 to the n, 1 to the n, 0 to the n language. Because essentially what is going on, so this is start 0011, right? That's our starting configuration. So these are equivalent. And we have now transitioned to, I have to look up what that state is, to seek 1. So we're now in seek 1. We have written a dollar, 01100, and we're at position 1. Here we are still in seek 1. This hasn't changed. Now position 2. So you can see that the computation is equivalent, and all we're really doing is we're replacing strings. So we're going to do one more. So we would now seek here. We would now find in this table a rule that matches the highlighted one. And that will be this one. So we're now going to replace with this. Still going to the right. Erasing this. So the configuration now is this state, which is seek 0. And I believe we have written an X here now. Yeah, we've written an X. So that is our, and we're now at position 3. And if we go all the way back up, I mean really all the way, sorry, then essentially, if you look at the first 4 parts of this computation, and instead of the triangle, just have 0, 1, 2, 3, then that is exactly what we are having and what we are doing here. And then the Turing machine ends whenever we reach this state. So there will have to be a check for that. Just trying to see where that is here. Yeah, I'm not immediately finding it. Maybe I didn't copy everything. Oh, that's what we're writing. I need to look here. All right. Oh, so here, whenever this rule applies. So from here, we eventually would go to accept, and then we would end, and then you would go into an accepting state. And I find this, while it's very tedious and complicated, I find this kind of cool. So once you've coded up you can just give it any Turing machine's description and input, and it'll just start simulating it, only doing these string substitutions, so to speak. So that's what I had on universal Turing machines. Questions? All right, so you might ask yourself, why? Well, first of all, it's kind of a mathematical model of computation. So we have very clear defined rules of what a Turing machine is and what kind of computation we can do with that. So it's a mathematical model for computation. And so far, we've looked at deterministic Turing machines, right? So that's exactly, if you see this symbol and you're in this state, then write that symbol, go to that state, and move to the left or the right. We've omitted some arrows from this. So essentially, it just said that everything that's not specified just goes to the reject state. So if we included that everywhere, that'd be a bunch of arrows just going to the reject state. But it doesn't add anything to the actual understanding of the Turing machine. That's why these are left out. But essentially, there's a clear rule. If you see this when you're in this state, then do that. So there's something called a non-deterministic Turing machine as well. And just like with non-deterministic state automata, you could then say, well, if I'm in start and I'm seeing an X, maybe I want to go allow this too. So on X, and maybe write something else and go to the left, right? But now when we're in start, we now have 2 rules for X. Just like a non-deterministic finite state automaton, we could have multiple rules to transition states from a state. We could also do epsilon stuff if we wanted to. So without seeing any input, just write something to where you currently are and move to the left or the right. So, so you might ask yourself, why? Why would we do that? Well, with the deterministic Turing machine um, or automaton, the computation was pretty clear. So you only have one choice. So if I wanted to draw that, um, that essentially we're going from one state, and it's not meant to be an automaton, but if you just do state transitions on an input, it's just a linear thing, right? We're transitioning from here to here to here to here, back here, 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 here. So it's a linear progression because you only have one choice everywhere. With a non-determinism thrown in, just like with um, NFAs, so I'm just going to scroll up to kind of remind us. So, oh, that's the wrong PDF. No. Oh, okay. Just to remind us. Yeah, I gotta go way up more with the. We talked about NFAs. So all the transformations, conversions. That these were all the possible computations that an NFA could do on just one input. So we're getting this tree here, and then we would have to see, ooh, when are we going to reach an accepting state here? But we would still say, even though there is the possibility of getting stuck if you make the wrong decisions, we're just going to assume that, well, if there is one path here to an accepting state, then we're going to say that this NFA accepts this input. And we can apply the same reasoning to non-deterministic Turing machines. So a computation in a non-deterministic Turing machine is going to be a tree like that as well. And we're just going to say, well, it just luckily makes the right decisions to go to the right ending accepting state to perform the computation. And essentially, you can compute things faster that way. And I'll come back to that. So if you have looked at the open DSA reading, then we are going to talk about MP completeness eventually. But I first have a few things that I want to define. So if you talk about complexity classes, and some of you may have heard of this before, and maybe your data structures class, I don't know. Technically, it's not supposed to be covered there. So we are now talking about how long does it take to solve a problem? So in 240, you have probably seen many problems that you have solved, like sorting or finding the minimum element in an array. We've seen some graph problems, right? Getting the minimum spanning tree, finding a path, performing breadth first search. So these are all problems that we have seen. And for the most part, we could do like okay, this problem, so sorting, bad example, is big O of n log n, right? Big O notation sounds familiar. And just trying to remember other things that you might have seen in 240. Have you guys seen any quadratic problems that can be solved in quadratic time? I'm kind of struggling remembering one too that absolutely is. quadratic matrix multiplication is big O to the third power. Right, and you may remember how you got these, right? That was an algorithm that was either a recurrence relation or a bunch of sums, and you could just say, okay, for the most part, it's actually big theta as opposed to big O, like that. And all these, we're going to consider that they're polynomial time algorithm. So whenever it is, when you have some polynomial here, and log n multiplying by log n does count as a polynomial, because strictly it is not, but you can kind of bound it between n and n squared. So we count it as polynomial time. So if you now have a deterministic Turing machine using a polynomial amount of computation time, then all these problems, we're going to say that they're in the class P, which stands for polynomial time. Since this is theory of computation, we are mostly looking at decision problems. Right? We've mentioned this before when we talked about some of the graph algorithms and problems. Right? It was the the Hamiltonian cycle problem, and then there was the decision problem. So one just said, does one exist, yes or no? And the other one actually wanted the solution from the problem. So we're back to just these decision problems. So if you have a deterministic Turing machine that uses a polynomial amount of computation time, then that problem is in the class P. So these two problems here would be in the class P. So there are some problems that you may know about that are not in P. Can you tell me maybe a problem that is not solvable by a deterministic Turing machine using a polynomial amount of computation time? Anybody remember anything from 240? Been too long. Who's done Towers of Hanoi? Who's familiar with that? Right? Not really buying that, but fine. It might have been too long ago. So Towers of Hanoi essentially said, well, I've got 3 pegs here, and we've got disks on there. And they might look like this. So this is where I start. So I got 3 in this example, 3 disks that I pile up on each other. And the problem now is I want to, and they're heavy, super heavy clay disks. I want to move these disks from peg 1 to peg 3 by only moving 1 disk at a time. So that is one constraint. And I may not put a larger disk on top of a smaller disk. So I could take this disk off and put it here like that. And now if I take this disk off, then I'd have to put it here. And then I probably have to take this one and put it up here. Now I can move the large disk like that. Then I can move this one back here. Move this one here. And finally, move that one. Here. And ta-da, well, I guess I'm a little crooked. I've done it. And you can set up a recurrence relation, so you can recursively solve this by saying, well, I can break this down into I first move n-1 disks onto some peg, then move the big disk on my target peg, and then move n-1 disks onto that as well. And then you can count the number of moves, and it turns out that this is theta 2 to the n. And this is no longer a polynomial because it doesn't have n to the something on there. So Towers of Hanoi is not in P. So it'll actually turn out it's not an NP either, but that was not my point. It was just an example of a problem that is not in P. So there are other problems that I already told you that are hard. So we, in particular, we looked at Hamiltonian. So cycle and traveling salesman. And currently, the algorithms we have for these are also not polynomial. But we're kind of now coming to a point where we kind of want to see, well, can we do better than what we currently can do with this or not? So note, I'm not writing this next to these because we actually don't know whether or not they are in P. So there's now a new class, which stands for non-deterministic polynomial. That's what NP stands for. And it is the set of decision problems solvable in polynomial time by a non-deterministic Turing machine. So that means we can now kind of start at a state and perform a computation. Let me just annotate. So we can have a start state in our Turing machine, and we can now branch off like that and perform computation. So these would be the possible computations performed by a non-deterministic Turing machine. And eventually, there might be an accepting state that is being reached here and maybe here as well. So you can think of these as many parallel computations that are being done concurrently, and then that the non-deterministic Turing machine is just making the right guess at the same time. So we can reach this thing here in polynomial time and perform this computation. So that is what it is supposed to capture here. So these exist on a theoretical level, right? We've seen non-deterministic automata. I told you what the non-deterministic Turing machine looks like. But if you can't really, we don't have computers that are non-deterministic because you can't just guess the right thing all the time. So we can simulate non-deterministic Turing machine by kind of enumerating all the possible transitions you can make and all the possible transitions. So I can draw that tree, and then we can kind of inspect all the leaves and all the paths to the leaves of these trees, and essentially simulate a non-deterministic Turing machine by that, but at that point we probably lost this polynomial time aspect when we do that. Um, so great. So there's this class NP. So clearly, the class P is a subset of NP, right? If I can solve it by a deterministic Turing machine, then certainly I can solve it with a non-deterministic Turing machine. It's the same reasoning that a DFA is already an NFA, right? It's just happened to be a deterministic one. Similarly, a deterministic Turing machine can be considered a non-deterministic Turing machine, trivially. One thing, though, that is important now is that when you have a solution to a problem that is in NP, then the solution is verifiable in polynomial time by a deterministic Turing machine. So that means we can follow this path that actually leads to the solution. And because we required that it was solved in polynomial time by a non-deterministic Turing machine, then taking this one path that leads to an accepting state, that must be in polynomial time. And in polynomial time means if you increase the input, make it larger, then this path grows only by some polynomial of that input size. So we know that we have to be able to verify a solution in polynomial time. So whenever we can just guess the solution to a problem and verify it in polynomial time, then that problem is in NP. So Hamiltonian cycle is in NP. Traveling salesman is in NP. So you can kind of guess the right solution, and then you can always verify in polynomial time that, yep, that's the Hamiltonian cycle, or yep, the route for this traveling salesman is smaller or equal than some k. So these are in NP. So the big question now is P a proper subset of NP, or is P equal to NP? And we don't know the answer to that. So for this reason, we now have the class NP complete. So we're going to take it one step further and say a decision problem is NP complete if, first of all, C needs to be in NP, and every problem in NP is reducible to C in polynomial time. Well, what the heck does that mean? So this is where problem reduction comes in. I'm keeping an eye on the clock here. So we kind of have to first see what this reducible stuff is. So when we talk about problem reduction, no. I have select things here that I take from OpenDSA. We are not quite there yet. So problem reduction, and I apologize for typing. Like I said, we were kind of doing the condensed version of things, so I don't really have any good readings to follow here. So you can say A reduces to B if step 1, you transform input to A to an input to B. Step 2, you solve with a new input. And step 3, you transform the solution of B to a solution of A. So essentially it means we have a problem of type A, but we're going to use an algorithm for B to solve it. So that is problem reduction. And we need to perform these 3 steps. And if all these 3 steps here can be done, well, if this transformation here can be done in polynomial time, and this transformation can be done in polynomial time, then we say that A is reducible to B in polynomial time. So this is very abstract. So I tried to come up with really good examples, but I only could come up with lame examples. So let's say problem A is finding the maximum element. Actually, I'm hesitating because that is really lame. Element uniqueness. So given an array of integers, are all elements unique? And let's say problem B is sorting. So I can solve the element uniqueness problem by applying it to sorting. So step 1, in this case, I actually do not need a transformation. Because both of them just take an array of integers as input. So step 2, sort the array. Now, however, I have a solution for B, a sorted array. So now I still have to kind of transform that to a solution of A. How would I do that? So how do I determine now whether or not all elements are unique? Well, I can just iterate through the sorted array and check if adjoining elements are unique or not. Right, since I've sorted them, I only have to now look at the neighboring elements. And since no transformation was necessary, this is constant time. And this here, I only have to iterate through the array once. So this is linear time. So I can say that element uniqueness is polynomially reducible to sorting. Yay. And yeah, we can do this to actually build algorithms, right? I have an algorithm for sorting. I not necessarily have one for element uniqueness. I mean, you could do a square n square algorithm, right? You look at the first element and see is it in the array, and then look at the second element, see if it is elsewhere in the array. Um, but I could just say, well, I'm not going to do these transformations instead and apply the sorting algorithm to it. So sometimes this is being done to get solutions to problems that you are not sure about, or that, like I said, you have an established algorithm for something and you just quickly can apply that. More commonly, these reductions are occurring in the theoretical computer science realm, though. So, so we can now come back to this. And we now have a problem C that is in NP. And if every problem in NP is reducible to C in polynomial time, then we call this an NP-complete problem. And if you think about that, that's quite something, which essentially means that we can use C to solve every problem in NP, right? We can solve the Hamiltonian cycle problem with it, and the traveling salesman problem with it, and sorting, and matrix multiplication, and element uniqueness. They're all in NP. And you would think that there wouldn't be any of these things, but actually it has been proven that at least one of these actually exists. So now I'm switching here. So where are we? I was just looking for the historical reference. Was that in here maybe? No. I was about to say that Cook actually proved. So there's a circuit satisfiability problem. Yeah, that I looked at it, but I want to show it here. Was it here then? Yes. So Cook proved that the circuit satisfiability problem is NP hard, and NP hard just means that every problem in NP is reducible to C in polynomial time. So it doesn't necessarily need to be in NP itself. Then we call it NP hard. That's this node right here. So there was an actual proof. He proved that every problem in NP can be solved by reducing it to this circuit satisfiability problem. When I was a grad student, I actually had to look at that proof, and it was long and it was convoluted, and I don't think I gained much from it. So clearly, proving that is way beyond the scope of this class. However, now there is this one problem. So SAT, like that. And now what people then did to find more problems that are NP complete is they just reduced SAT to those problems. So first of all, let's introduce some shorthand notation. I always get it exactly wrong. So I think this will be a symbol. I think the greater, it might be the smaller symbol, but I think this is the correct one. So if you use this notation, if you can now find a problem, so if I want to find more of these, so I can now say if C is in NP and SAT polynomially reduces to C, then C is NP complete. Because I'm essentially then saying, well, I can solve SAT by solving C, and I can solve every problem in NP by solving SAT. So by a transitive property here, I can then just say that every problem in NP is also reducible to this new C problem if this part here holds. So it's just part of my transformation then. So we can chain these things together. So I can solve traveling salesman by reducing it to SAT, and I can solve SAT by reducing it to C, and all these transformations are in polynomial time. Therefore, I can solve traveling salesman by reducing it to C, because that is part of the reduction, this chaining together. So we're going to look at one of these transformations. So this is kind of the chain here. So people started doing that, right? So Cook did this one, and then I think Karp then said, okay, well, I can, this one reduces to SAT, SAT reduces to 3SAT, and then the clique 3SAT reduces to the clique problem, and so forth. So all these problems are NP complete now, and people are finding more and more of these NP complete problems, which in and by itself is not all that exciting, but you always have to prove something. So we're going to do 3SAT to clique. So first of all, let's look at these, and I'm keeping an eye on time, and whenever I go up here with my mouse, I'm getting the zoom menu, so I kind of need to move stuff around a little bit. I was going to make it a little smaller. No, not a good. So 3SAT is the 3CNF satisfiability. So we have a Boolean formula that contains AND clauses which are OR together. So you would have just these variables, x1 or x2 or x3, and then AND that together with this term and AND it together with that term. So the problem then is, can we find true and false assignments to these variables, x1 through x6, that make the entire term true? And it turns out that this is an NP complete problem. So if we just go through here, so we can just look at an example, and we can just look at the truth tables, right? So we have 4 variables. We can just look at all, whatever, 16, no, 16 possibilities here of assigning true or false. 16. And then just plug it in for P. And then indeed, an assignment here, here, and here exist. So the green ones, they make this true. And if we make this a decision problem, then it's just saying, okay, given this term here, is there an assignment of true and false to x1, x2, x3, x4 that makes the overall term true? In this case, yes, the answer is there exists at least one assignment that does that. So this P formula is satisfiable. That's where the 3 satisfiable thing comes in. And here's an example. If you enumerate all the truth tables, then none of them ever evaluate to true. So here, no, there is not an assignment of true and false. All right, still not all that exciting. So if you actually want to go the truth table route, then you have to come up with 2 to the n entries in your truth table. So that's why the current solution, and that's the best solution we have, by the way, for it, is exponential. So we don't have a polynomial time algorithm for this. So the clique problem, we've already talked about when we talked about graph algorithms. So a clique is a graph. So this is a complete graph. So they're all connected, right? It's like a complete subgraph. So when we look at this graph, then here's a clique of size 3, denoted in red. Here's another one. So then the question is, if you make it a decision problem, a given graph G, does it contain a K clique, where K is the number of nodes in the clique? And then sometimes you want the maximum clique. So here you have a 4 clique in the same graph. They're all connected to each other. So again, we don't have a good algorithm for this. So probably solving this, you kind of have to take all the subsets and see if they're all connected to each other, or stare at it for a long time. So in this case, apparently there's not a clique of size 5 or larger. There is one of 4 or larger, highlighted here. So that's the clique problem. And both are NP complete. And if we look at this chain here, so circuit set was the original, then came SAT 3 set. So people already proved that these 3 are NP complete. So if I can now solve the 3 set problem by transforming it to a clique problem and then solving the clique problem, then I will have shown that clique is NP complete. So how do we do that? And very smart people have come up with these. So these transformations, especially for the NP completeness ones, they're very tricky. So we're given a Boolean formula in CNF form, conjunctive normal form, by the way, which means we're ANDing the terms together. And we need to check whether it is satisfiable. So let's assume we are able to solve the clique problem. So we can reduce 3 set to clique. So we're going to construct a graph where we have K clusters, one for each literal, with a maximum of 3 nodes. That's where the 3 set comes in each cluster. And each cluster corresponds to a clause in the Boolean expression. And then each node in a cluster is labeled with a literal from the clause, meaning either X or not X, or X1, not X1, that kind of stuff. And then we're going to connect these nodes, and I'm going to explain this in more detail and see what happens. So if this is the literal, this is an example, then we have 3 terms, one for red, green, and blue, and we're just going to create nodes for them. Each one, x2, x1, not x3, corresponding to these OR together terms. So we're going to do that for all 3 terms, and that can be more than 3 terms, but only 3 literals within each cluster here. And we're not supposed to connect, meaning drawing an edge between any of these. So x2 would have to connect here, and here, and here, and here, and here, but not, that's the only exception, if it's a negation of itself, then we're not going to draw an edge. So if you do that, then x2 connects to all these guys, then x1 will connect to everything but this one, not x3 will connect to everything but this one, and we now have to still continue with x1, so we're just going to continue, and now we're done because it's an undirected graph. So this is now our graph, and the inside here now is there's a connection here whenever any of these can be true at the same time. And that's why we didn't allow this edge, because x and not x, or sorry, x2 and not x2 can never be true at the same time. So these are now all the possibilities of simultaneous truth assignments. So you can say x2 can be true when x3 is true, and x4 can be true, and not x3. Well, we have to see how it chains together. So these are possibilities. So this is now the graph we have constructed, and we have now transformed this input here to an instance of the clique problem. So if you now find a clique of 3 in this graph, then we will have found a solution. So if 2 nodes in the graph are connected, corresponding literals can be simultaneously be assigned true. If 2 literals not from the same clause can be assigned true simultaneously, the nodes corresponding to these literals in the graph are connected. And we can do this in polynomial time. And now the claim is that G has a k-clique if and only if the term is satisfiable. So if it has a k-clique, then the clique has exactly 1 node from each cluster, because no 2 nodes from the same cluster are connected. So if I just go back, so we never drew any edges between these cluster nodes. So anything that is strongly connected, there can be only 1 member of each cluster in there. And all nodes are connected, and they can all be true simultaneously, which means that each literal belonging to one of these clauses, and therefore there is a solution for that. So here we have 1 clique of 3. There's many actually. But if you just say if x2, x4, and x3 are true, then since all of these things are ORed together within each group, that makes the entire red group true, the entire green group true, and the entire blue group true if just these 3 are true. So this is a possible truth assignment. And now we have transformed that into a solution of the original problem. And like I said, people now did all kinds of stuff. So Hamiltonian cycle, traveling salesman. So there's more here in the OpenDSA reading. You can look at many of these transformations. So there's now this large collection of NP-complete problems that can be used to solve any problem in NP. So you might say, so what? Well, if you're now coming back to this, and we don't know the answer to this, but people are looking. If you find an answer to this, by the way, you can get $1 million. There's a prize out on one of the millennial problems. And you can get instantly famous. But if I now just say, if I can find a reduction So um, if I can show that a decision problem C, if C is NP complete and C is in P, then you will have proven this. So, because that essentially means that I can do any problem in NP, and we can polynomially reduce it to C, and C has a polynomial time algorithm. So we can first, in polynomial time, transform the input, then solve B, or C in our case, in polynomial time, and then transform the input back in polynomial time, which means we can now solve any problem in NP using C in polynomial time. So if you can find one problem like this, then you will have shown this. People suspect that they're not equal. So people suspect that this is actually true, but nobody has been able to prove that. So, but it's still open. So if somebody finds this, then all of a sudden, some of these problems where we don't have a good solution for it, right? Like enumerating all the possible cities in exponential time and then checking or calculating what the cost is, um, then we could have more efficient algorithms for all this stuff. So that's what a good number of theoretical computer scientists are still doing, is kind of looking at this problem. And then there's other problems for which we don't have time to discuss, where you can even see where we can't compute them at all, like the halting problem. But we definitely do not have time for that in this class. And this is about as far as I wanted to get with you, to just kind of this very open question in computer science. And if it actually should turn out that this is true, we could actually build better algorithms. And that could then affect the whole cryptography stuff that we've seen in module 1, right? Most of these things depended kind of on the assumption that this is true. And because most of them were NP complete. So discrete logarithm problem is NP complete. So if somebody finds this, then we can just crack RSA in polynomial time. So who knows? All right, so that was a lot to digest. I just wanted to at least kind of get everything well-rounded. And like I said, I'm not gonna test you on this, but you should have at least seen this before. So thank you for sticking with me today. And also thank you for sticking with me through the semester in these hard times. And if you have questions about this, then please ask now. Or if you have any other questions, I'll still stay on for office hour. And again, thank you for being with me this semester. And I hope you stay safe and healthy during the next few weeks. And maybe next semester we'll be able to see each other in person again. All right, so I'm going to stop recording. I'll stop sharing, stop recording.